Okay, so this video is going to be a little different. It's on the whiteboard because I forgot about chapter 7, your cell membrane. Can you believe that? Who would forget about cell membranes? So this one's a little impromptu, a little last minute. I'm going to try to do my best though. So chapter 7 is all about the cell membrane, and I have drawn a gorgeous cell membrane right here. You can see it here. You may remember that the cell membrane is a phospholipid bilayer. So if we zoom in here on one of these guys, we have our phosphate. Oh, this is rough. We have a phosphate head, and we have our fatty acid tails. So you may remember that this phosphate head is polar, and these fatty acid tails are non-polar. So polar and non-polar describe charge. Polar has some charges, non-polar has some charges. We're going to switch these terms just a little bit. You probably already heard it. We are going to call polar, instead of calling it polar non-polar, we are going to refer to it for the rest of this video. I'll probably call it polar and non-polar a few times, as hydrophilic head and a hydrophobic tail region. Hydrophilic means water-loving. Hydrophobic means I'm scared of water. So when we put a bunch of these phospholipids into a cell membrane, they're going to orient in this very specific bilayer way, because on the outside, or extracellularly, we've got water. I'm going to go ahead and erase this gorgeous drawing. And then on the I'm going to scoot this forward just a bit. Make sure. Still in frame. That's great. And then on this intracellular portion, we also have water. So these hydrophilic polar heads want to be by the water, which is on the outside of the cell and inside the cell. And these hydrophilic heads, and then these hydrophobic tails want to orient themselves inward away from the water. They're protected by the water from these phosphate heads, forming, essentially, we have the first layer of heads, which are going to be hydrophilic. Then we have all our hydrophobic tails, and we have another layer of hydrophilic heads. So that's the cell membrane. The first thing that we need to discuss is fluidity. And for this, I am going to go over here. Ignore all this for now. It's coming. Let me make sure I'm in frame. I'm in frame. We're so good. Okay, so we are going to talk about fluidity. Fluidity means exactly what it kind of sounds like. It means how fluid is our cell membrane. I can't draw it, unfortunately, because I am no artist and I don't have the time, frankly. But if you look at a whole cell, the cell membrane encases the whole cell. It's a sphere. We draw it like this because 2D, and we teach in 2D, but it's a 3D structure. Remember, a cell is a 3D structure. So if you look down on a section, if we're looking from the top down, like this, if we're up here looking down, you are going to see a whole bunch. I'm going to draw a very small portion of it. You're going to see a bunch of hydrophilic heads, and you're going to see some accessory structures like proteins. We'll call this square a protein. You might see some glycoproteins as well for cell-to-cell communication. You could see a lot of things, but the point is, it's called a fluid mosaic because all of these phosphates, or all of these phospholipids, but we only see the phosphate heads, are able to move around. They can sort of squish in between each other, and we call that fluidity. Fluidity means how well can the membrane move? How well can each of these phospholipids move about? So all we need you to know, we're going to talk about what increases and what decreases fluidity. So I'm going to just write down a few things really quick. If you want to write them down with me, we're going to talk about cholesterol. We're going to talk about unsaturated fatty acids. We're going to talk about temperature. Those are the three that I'm going to talk about, and these are the three most important. Unsaturated fatty acids, cholesterol, and temperature. So, back to the big drawing. Is it in frame? It sure is. In and amongst these phospholipids, specifically in the tails, in the hydrophobic tails, we are going to have some random clumps of something. And these clumps are cholesterol. So cholesterol is going to embed in the membrane. So cholesterol can actually affect fluidity in two ways. What I want you to think about cholesterol is that it resists change in fluidity. Oh, I've hit the border, people. Doop, doop, doop. There we go. It resists changes in fluidity. It wants the membrane to stay at a certain point, and I'm going to sort of take two pathways for this that we're going to talk about and think about it logically. So cholesterol, let's talk about if the phospholipids are getting really close together. So if they're kind of, I hope this is in frame. If these phospholipids are packed really tightly together, like so tightly that they just look so jumbled, it's not going to be very fluid. The cell membrane is going to lose fluidity. It's going to become more static because these phospholipids don't have space to move around. What cholesterol can do in this situation is it can jump right in here. I'm just going to use the last one as an example. Cholesterol can jump in here and force a little bit of space. So now, imagine we put a little cholesterol throughout all of this. Now we have more space. So we have more fluidity. We have resisted the decrease in fluidity. So when phospholipids pack too tightly together, cholesterol says, whoa there, buddy, we're getting a little close in here. Why don't we break it up a little bit? And they break up the phospholipids to create space, which creates fluidity. So that's one situation. But let's think of another situation. Let's think of this situation. So in this one, our cell membrane is really, really fluid. Look how spread apart these phospholipids are. If it gets too fluid, that's going to create a problem. If there's too much space between these phospholipids, anything can just get through. Pathogens, antigens, horrible things could get through. We don't want that. So what cholesterol will do here, when the membrane becomes too fluid, is cholesterol is going to grab onto these tails and it's going to pull these together just a little bit more. It's going to say, whoa there, you're getting a little too far apart, and it's going to pull them back in. In other words, it's going to resist the increase in fluidity. So cholesterol, in some sense, is always an oppositional force. If fluidity, sorry, I'm taking an aside, fluidity, cholesterol. If fluidity decreases and those phospholipids get packed really close together, cholesterol is going to fight that by trying to increase the fluidity. But if fluidity is going absolutely crazy and those phospholipids are just super spread out, cholesterol is going to try to fight that and decrease the fluidity. So cholesterol resists change in fluidity. That's what you need to know there. Next up, I want to talk about unsaturated fatty acids. So I'm going to draw two phospholipids real quick here. They look very similar with one difference. This fatty acid right here has a little kink in it. And you may remember, a kink in a fatty acid means it's unsaturated. That's happening because the carbons are not fully saturated by hydrogen. You don't need to worry about why. It creates a little kink. So I want you to imagine if I have no unsaturated fatty acids in my phospholipids. Look at this. They can pack really tightly together, which is going to decrease fluidity. But if I throw in a couple, and we'll do a very dramatic one here with two unsaturated fatty acids, these kinks are kind of creating space, for lack of a better term. They're forcing a little space. It's kind of like if we have all saturated fatty acids, it's kind of like standing cramped in an elevator with your arms at your sides. You can't spread out, you're cramped together, you can't move around, you're not very fluid. But these unsaturated fatty acids are kind of like, we're on the couch now, we've left the kitchen, are kind of like, you're relaxing, you're kicking back, you're spreading your legs, your arms, you're spreading your arms out, you're comfy. That creates more space. You're taking up more space than you were when you were cramped in that elevator. So that increase in space is going to increase fluidity. So, just to put that into words, firstly words, as we get more unsaturated fatty acids, fluidity is also going to increase. So the last one I want to talk about is temperature. Temperature is kind of intuitive. It's exactly what you think it's going to be. And remember, this temperature is always going to be like oppositional to cholesterol, sort of. When temperature drops, if it gets really cold, so this one over here is going to be increasing, that's going to be hot, this one's going to be cold. So if it gets really cold, it's going to slow the speed at which those phospholipids can move. Kind of think about it like if you go out and when your hands are really, really cold and you try to go like this, you can't do that as well. You can't really, your muscles are slower. You're slower. Same thing with the cell membrane. It's going to decrease fluidity because because if those phospholipids can't move around as well, then they're not going to be as fluid. They're going to sort of freeze. You can think about it kind of like that. They're not actually going to freeze, but they're going to slow down. Inversely to that, if it's super hot out, when it's super hot out, your muscles are ready to go more. Your muscles are, warmed up, kind of. So that's going to increase fluidity. It's going to mean that those phospholipids can move around faster. All right, so that's fluidity. Remember, cholesterol is going to resist changes in temperature or changes in fluidity in general, so it's always going to be sort of oppositional. If we have unsaturated fatty acids, that's going to increase fluidity. The more kinks we have, the better. Temperature, if it gets really cold, membrane's going to freeze, not going to be very fluid. If the temperature rises, it's going to increase our fluidity. Those phospholipids can move around really well. All right, so that's fluidity. Next up, and this is the big one for this chapter and the only other topic, I hope. Again, I'm sorry for the impromptu-ness of this one. I didn't have anything prepared note-wise. But we're going to talk about transport. So, transport, remember this cell membrane, extracellular, we have stuff. Intracellular, we have stuff. What if we need that stuff to get through this membrane? That's going to be transport. Transport just means we're moving things through the cell membrane. There are two kinds of transport. There are some subcategories, but the only two kinds of transport that you need to worry about are passive transport and active transport. So, passive transport, I want you to think two things. High to low, no energy. Let's do a little partition there. So passive transport, hold on, let me make sure we are in frame. Oh yeah. Passive transport is going to be high concentration to low concentration, and you do not need to put energy in to passive transport. Passive transport is just gonna happen. Active transport, though, is going to go from low concentration to high concentration. And that is going to require the input of energy. So that's the difference. Passive transport, we are going from high to low concentration. Active transport, we're going from low to high concentration. And then passive transport, we do not need to put energy in. Active transport, we always are going to need some extra energy to help get it going. So let's think about this. Let's think about passive transport. I always like to think of it as you have a cup of coffee. This is coffee. And you add a splash of cream to it. So that cream, it's not going to go like, it's not just going to like ball up right here and then all your cream is right there. No, it's going to diffuse. It's going to diffuse and it's going to make your coffee a little lighter. Like that. Right? So that's passive transport. I didn't have to put energy in. I just added the cream, and once the cream was in there, we were good. You know, that was it. And I apologize. I need to go grab a new paper towel. Sorry about that. So, diffusion. We're going to talk about diffusion. Diffusion is a form of passive transport, so these conditions remain true. Diffusion is going to be directly through the membrane. Sorry, I'm pulling this side again. Handwriting's terrible. Diffusion is directly through the membrane. That means just regular, simple diffusion means I'm just going to take what I want to transport and I'm just going to pop it through like that. Nice and easy. But while we're talking about this, I'm going to pull the other board, I want to talk about what could do simple diffusion. So here we have a couple molecules, 4. I have CO2, I have O2, I have glucose, and I have a triglyceride. So we are going to talk about the conditions under which something can pass through the membrane, just directly through the phospholipid bilayer. It needs to be. So to pass bilayer, and this means pass directly through the bilayer, guys, directly through the bilayer. You need to be small. You need to be non-polar, and it goes kind of without saying because we said non-polar, but you need to be uncharged. It's all in frame. It's not. There you go. To pass bilayer, you need to be small, non-polar, and uncharged. Let's talk about why. So here I have CO2 and O2. These are things that can pass right through the bilayer. And when we look at the molecular structures, you see that they are nonpolar. You'll just have to trust me. If you want to do the math, you can, but there's no dipoles, there's no partial charges. They're both pretty small. You know, CO2, that's 3 atoms. 3 atoms is pretty little. This one's only 2, so that's super, super small. And then uncharged, yep, they're uncharged. So these two things can pass through. Cha-ching. But when we move down here to glucose, well, glucose has all these OHs on it. And all of these OHs have negative charges. So this is a polar molecule. Let's put that in parentheses. Polar. Since it's polar, it can't get through. No to glucose. So it can't just pass directly through the bilayer. We'll get to how it gets in, though. And then lastly, we have a triglyceride. All right, triglyceride is nonpolar, so it should be able to get through, right? Wrong. Triglycerides are huge molecules. This huge molecule isn't going to be able to pass through here. It can't do that. It's cheating. It'll need to find another way in. So that is diffusion. Directly through the membrane, but they have to be small, nonpolar, uncharged molecules. Let's talk facilitated diffusion next. Let's say I do have a big old polar molecule of glucose. Can it just go through? We already said, no, it can't, no way. So it's going to utilize facilitated diffusion. So this uses a channel. Now a channel is going to be a channel protein. So glucose, instead of going through the bilayer, and I'm going to erase some stuff here, you know, make a new thing. Glucose is going to go through specifically the GLUT receptor, or the GLUT receptor, channel, whatever it is. Let's say that it's a channel. We're calling it a channel because I said channel. So this channel is going to be wide enough for glucose to go through, and let's say the inner regions of this channel are also polar. So the polarity that glucose had no longer matters. The size no longer matters. Glucose can go ahead and get through here. But very importantly, it is still moving from a high concentration, these brackets mean concentration, to a lower concentration. It's still moving down its concentration gradient. If there's a lot of glucose out here, and not a lot, so there's not much glucose out here, or sorry, I apologize, there's a lot, there's much glucose out here. This is your blood, let's say. We need that glucose in the cell, and there's not much glucose down here. Glucose can get in, no problem. We don't have to put energy in because it's moving from a high concentration to a low concentration. Osmosis is going to be the movement of water specifically. Movement of H2O to balance solute. We're going back to the mini board for osmosis. So let's imagine that we have a membrane that has absolutely nothing to get sodium ions through. I'm going to draw this membrane very crudely. This is the membrane though. So extracellularly and intracellularly. So we have very low sodium inside the cell, and we have very high sodium outside the cell. So if we have super high sodium outside the cell and super low inside the cell, sodium wants to get in here. But sodium has no way to get through this membrane. We're going to pretend there's no sodium channels, because sodium can get through if there was a lovely little sodium channel, but there's not. Let's say there's not. So sodium can't get through. Instead of sodium moving from a high concentration to a low concentration, what's going to happen is water is going to try to balance this. Because water, even though it's polar, I know what I just said, but water can get through the cell membrane. Deal with it. Water can move through this membrane, we're saying. So if I have a high concentration out here and a low concentration in here, which side is more diluted? It would be this side, right? Think of sodium as salt. This water is just a little salty on the inside. This water is super salty out here. Super salty. So how can I make this super salty water not as salty? I can add water. So since this sodium cannot get through to move down its concentration gradient, water is going to dilute the high concentration. And as water is added here, this concentration is going to start to lessen and lessen and lessen. That's osmosis. Osmosis is the movement of water through a semi-permeable membrane to balance solute concentrations. So let's think about this though. We have high sodium outside the cell, we have low sodium inside the cell, so water is leaving my cell. What's going to happen to my cell? If I'm losing a bunch of water in my cell, which once looked nice and healthy like this, is going to shrivel up because it doesn't have enough water now. The water has left, so the H2O has vacated the premises, and our cell has shrunk. Is this in frame? Good. So this cell would be considered now to be all shriveled up. The word for this is going to be hypertonic. This is a hypertonic cell, meaning tonic, essentially, well, you don't need to know why. It's hypertonic, is shriveled up. Hypertonic means that the solution outside of the cell has a higher concentration than inside the cell, so water leaves. So this situation that we've described is hypertonic, right? Hypertonic. And then let's imagine that we just flip these sodium gradients. Let's say that outside the cell we have very low sodium, and inside the cell we have super high sodium. Where's water going to go? Remember, there's water on both sides, right? So if I have super high sodium inside the cell, I have salty, salty water inside the cell. How do I dilute that salty water? I add water to it. Water is going to go into the cell. So if water is going into my cell, what's going to happen to my beautiful cell, my beautiful normal cell? It's going to swell up a bunch. It's going to swell up a bunch because water is going into it. This situation is hypotonic. Hypotonic. This cell is hypotonic compared to the solution it's in. And also hypotonic and hypertonic are always relative to the solution that the cell is in. I remember it by saying hypotonic, hippo. This cell swells up like a big fat hippo. Hypotonic. And then if things are perfectly balanced, we would call that isotonic. So that's what we want to be. We want to be isotonic. And that's osmosis. Let me check my time here. Oof, we gotta hurry. All right. That covers passive transport. Let's move to active transport. So active transport, we have been moving with passive transport from a high concentration to a low concentration, or down the concentration gradient. Active transport is going to go low concentration to high concentration. So we're pushing things. We're pushing things against their concentration gradient. And if we're pushing something against its gradient, it's going to require energy. Primary active transport, I'm going to write all the definitions down now, and then we'll go from there, uses ATP. Secondary active transport uses ATP indirectly. And secondary transport, it uses ATP indirectly because it's going to piggyback off the work of primary active transport. So secondary active transport is reliant on primary active transport always. Symport and antiport are going to be terms that describe the movement. Symport means we're moving two things in the same direction. So you can think of sim is same, sim, similar, same direction. Antiport is just going to be the same thing, but opposite directions. So symport and antiport are going to be usually forms of secondary transport. We're going to, and I'll just do examples right now. Primary uses ATP. The number one example that we're always going to use, it's going to be on tests, it's going to be in every bio class you take probably, it's in cellular bio, it's in neurobio, is the sodium potassium pump, or ATPase. So the sodium potassium pump, or ATPase, right? Hopefully you got the name down. We're going. So it is going to be this molecule, and I'm going to give us some pre-existing conditions. I'm going to say that concentration of sodium inside the cell is very, very high, and sodium outside the cell, potassium inside the cell is very high, and sodium is going to be much higher outside of the cell. So if I told you that active transport moves things from low to high, so we have low potassium outside the cell, and we have low sodium inside the cell. So active transport is moving it from a low concentration to a high concentration. So that means that we're pushing potassium into the cell against its gradient, and we're pushing sodium out of the cell towards its higher concentration. And that is going to require ATP, which will then convert to ADP, adenosine triphosphate, to adenosine diphosphate. So the sodium potassium pump in particular is going to move 3 sodiums out and 2 potassiums in. And it's going to do that by utilizing ATP. If you need to remember that it's 3 sodium going out and 2 potassium coming in, I always think of, it's the Rihanna song that goes, na na na, come on, that's the one. Na na na, 3 NAs, NA, 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 na na na. That is the sodium potassium pump. 2 potassium into the cell against its concentration gradient, 3 sodium out of the cell against its concentration gradient, using ATP as an energy source. So now secondary active transport. I'm going to keep that there because it's going to be relevant. And we're going to make another thing over here. Funny guy, we'll make him look like that. And this is going to be the sodium calcium exchanger. Sodium calcium exchanger, if you don't need to know symport and antiport, you can if you want, I guess. But sodium calcium exchanger, if we're exchanging something, then they're going to move in different directions. So this is going to be antiport. So let's talk about sodium calcium exchanger. So I'm telling you this is secondary active transport. So you know we're going to be moving something from a low gradient to a high gradient. And we're going to indirectly use ATP. So let's say that we have the concentrations that we care about are Na plus and Ca2 plus. And I'm going to give them to you inside and outside the cell. So sodium is going to be super, super high outside of the cell. And calcium is going to be high outside of the cell too, right? They're both going to be low inside the cell. But if I were to ask you, why is sodium so high outside of the cell? It's because of the work that has been done by the sodium potassium pump. The reason that we have this gradient of sodium and that it's so high concentration outside of the cell is because this sodium pump keeps pushing 3 sodiums out and taking those 2 potassiums in. And it did that by using ATP to ADP. Right? That is what I mean when I say we are indirectly using ATP. Oh, I hope this is in frame. It's in frame. That's lovely. So the ATP is being used because we are harnessing the concentration gradient of sodium that we have created from this sodium potassium pump. And that's what I said when I said secondary active transport is dependent on primary active transport. So now that we have this super high sodium outside of the cell and high calcium, let's say that I want to take a calcium from inside the cell and move it outside of the cell. So I'm moving this calcium from a low concentration to a high concentration. That's active transport, and it's secondary. So we need energy for this because we're pushing the calcium we're taking, if you think of as a sad example, if you have a herd of cows and you have them in this very tight enclosure, it's very easy to take a cow out. You just open the gate and they'll spew out. The cows will all come out, but it's hard to push another cow in. But that's what we're doing. We're pushing this calcium into the high concentration. So we need energy. That energy is going to come from letting sodium that we have created a gradient for. We have increased the concentration through the sodium potassium pump. We're going to now let that sodium come back into the cell. And in that process, we're going to generate the energy that we need. And that's secondary active transport. An antiport, to be specific, because the calcium is going out, the sodium is coming in. So that is all I can really think of right now for membrane transport and cell membranes. Sorry for the impromptu video and how it's, it wasn't my normal notes, but I hope it was helpful, and have a good night.